Now we're going to talk about bootstrap confidence intervals. So, if you remember last time, we were talking about how we could find a 95% confidence interval. We would take a random sample from the population, compute the sample statistic, we'd repeat those steps many times, and then we'd find the standard error by finding the standard deviation of the statistics. But the problem is that we only get to take one sample. So we can't do step one many times, go back and take a random sample from the population, because that would be too expensive. So the question is, what are we going to do instead? And the answer is a technique called the bootstrap. So the name of the bootstrap comes from the idea of pulling yourself up by your bootstraps, which of course isn't something you can actually really do, but we're going to try and make something from nothing. And the example that I usually give if we are in class together has to do with M&Ms. So I am interested in determining what proportion of M&Ms are blue. And so, one thing that I could do is I could take many samples from the population. So, if I was in class, I would bring M&M packs for everyone, and then I would hand them out, and we would assume that those 90 packs of M&Ms were random samples from the population of all M&Ms. It's not quite a valid assumption because maybe they were all produced on the same day or at the same factory, so they might not truly be a random sample, but they're certainly samples. And then we would each open up our pack of M&Ms and we would compute how many M&Ms in the pack were blue. And so this would be a sample statistic, a sample proportion, p hat. So the last time I did this, I had 14 M&Ms in my little pack, and 3 of the 14 were blue. So my sample proportion was 0.21. So that's my best point estimate for the proportion of blue M&Ms in the population. If you said, how many M&Ms or what percent of M&Ms do you think in the world are blue? I would say my best guess is 21%. But I would feel more confident if I got to give an interval estimate. So one way that I could give the interval estimate is I could give out packs to all of you, and you would also have all of your little samples, and we could build a sampling distribution that way. But let's assume that I don't have all of you. I don't have 90 packs of M&Ms. All I have is my own 1 pack of M&Ms. That's my only sample. So what would I do in that circumstance? Well, what I would do is I would pretend that the population is just many copies of my original sample. So this makes the assumption that my original sample was a random sample and therefore it represents the population well. And if I was thinking about my 1 pack of M&Ms, here's how I might imagine the population. Really, I have to think of it as infinitely many copies of my sample, but I couldn't put that all on the slide. But here's many, many copies of my sample. And the way that we would simulate a sampling distribution is we would take repeated samples from the population, which is made up of many copies of our single sample. But again, in practice, we can't make infinite copies of our sample. And so our solution is to sample with replacement from the original sample. And that means you're going to draw out an M&M and record, is it blue or not blue? And then put it back and, stir it around again. So I could get unlucky and pull the same M&M every time, but probably I'm going to, draw some different random ones. But I'm doing the sampling with replacement, so I put the M&M back in the pile. And I'm going to do that, draw it, record if it is blue or not. I'm going to do that the same number of times as there are cases in my original sample. So in this case, I had 14 M&Ms in my original bag, and I'm going to draw out a sample with replacement 14 times. And I would call that a bootstrap sample. So a bootstrap sample is a sample with replacement from the sample the same size as the original sample.